real exam questions. It is question 33, and it's about beam design. Consider an isostatic beam, span L, in bending over a rectangular cross-section. Determine the minimum longitudinal reinforcement, AS1. Determine the minimum amount of stirrups, ASW. What is the capacity in ULST of a beam reinforced with the minimum stirrups and longitudinal reinforcement? The minimum longitudinal reinforcement and the minimum stirrups. Calculate the bending moment, the shear force, and the uniformly distributed load, including self-weight. So this is the section. There is, of course, compression reinforcement, which is the minimum reinforcement, but we will not take that into account in the total resistance of the beam because it's here simple bending. The concrete quality is 25 megapascal and the steel quality 500. Total depth of the beam is 600 by 300. And now we have to calculate first the tension reinforcement and the stirrups needed. We will now calculate the capacity in shear force by minimum shear or by minimum shear reinforcement. The minimum percentage of stirrups is given by this formula. We fill in the elements that we know, and we have 0.8 times 10 to the power minus 3. That's the ratio of the minimum amount of stirrups. The minimum amount, the ratio rho is defined as the stirrup ASW divided by F times B. So the needed stirrup reinforcement as minimum reinforcement is equal to B times rho, which gives you 0.24. When you take a stirrup with two legs of diameter 6 at the spacing of 235, we have 0.241. So it will be okay. Now we will first check if this center-to-center placing of the stirrups is not too large. For that, we know that the distance center-to-center must be smaller than 0.75 d, which means that S must be smaller than 411 millimeters. So this is okay because we are 235. D, what we have used it here, but D is 600 minus 40 minus the stirrup diameter, and we assume that the maximum diameter of the longitudinal reinforcement is diameter 12. Why don't we take 16, for instance? Well, this is a capacity of the beam that we have to calculate for a minimum reinforcement, so we do not expect very large reinforcement. But if 12 it was not okay, then we have to redo the calculation. The shear force that can be taken by the minimum shear force reinforcement is then given by this formula. Alpha is 90 degrees because we are using vertical stirrups. So cotangles alpha is 0 and sinus alpha is 1. And we take as cotangles theta equal to 2. Let's give you the maximum capacity. And when we put in the different numbers, we see that we have 103 kilonewton. Z, the lever arm for the shear force, is 0.9 times V, 0.9 times T. So the total capacity is 103 kilonewton. Now we look for the minimum tensile reinforcement. We have first to look for crack control. The minimum reinforcement needed for crack control is given by this formula. It is just that the minimum reinforcement must be able to take up the bending moment, to take up by the cracking bending moment. In this equation, sigma S is 500 megapascal, it's FAJ. Kc is the coefficient for bending, it's 0.4. For tension, it's 1. K is a factor for scaling, a scaling factor. It's an interpolation, and it gives you 0.79. And the FCTF, the effective tensile stress when the beam is going to crack, we've taken it as FCTM, which is 0.3 times the value of the compressive strength to the power 2/3, gives you 2.56 megapascal. The section under consideration is half of the section, which is 90,000. Bear in mind, if you use this as half, you have to put the reinforcement on top and on the bottom, because you can have also a cracking bending moment, a negative cracking or a negative cracking bending moment. So this is for the positive cracking bending moment. So ACT is 90,000 because of pure bending. Fill in the different parameters, and we have 146 square millimeters. Then we have also looked at the minimum reinforcement for brittle failure. It's given by this formula. All of those variables are now known, and when we calculate it, we find 219 square millimeters. So the minimum reinforcement is then the minimum of the one needed for neck control and the one needed for brittle failure. So it's 219 square millimeters. 2 diameters 12 is 226 square millimeters. So the diameter 12 that we have chosen in the beginning is okay. If not, you have to redo the calculations with the right diameter. So our section of the beam is then 600 by 300, 2 diameters 12 on top, 2 diameter 12 on the bottom, and the stirrups a diameter 6, center of center 235 millimeters, and 2 legs. Now from this section, we have to calculate the resistance or the bending moment capacity. We can now use the concrete tables. Just bear in mind, we are looking now for the bending moment capacity. So we cannot work directly with mu d. We know that what the reinforcement ratio, and we have the geometric characteristics. So omega is then equal to this, and it gives you 0.0422. So we look up in the table 0.4022, and we make a linear interpolation, and we find zeta, which gives you 0.9666. And from this, we can calculate the needed reinforcement, which is the bending moment divided by zeta dfyd. But the minimum reinforcement we know, needed reinforcement, which is 226. But we are now calculating the MD, the bending moment capacity. So MD is 226 times the lever arm 548 times the yield stress of the reinforcement times the lever arm coefficient. And to put it in the right units, it's times 10 to the power minus 6. So the bending moment capacity is 52 kilonewton meter. Now we have to determine the load QD. Of course, it's a simply supported span. So the maximum bending moment in the middle is QD L squared over 8. We know what MD is, that we already calculated, so that must be 52. The shear force in a simply supported beam is QL over 2, and we know that the maximum shear force that we have calculated for the minimum stirrups is 103 kilonewton. You'll see that to find the load QD, we need span, but we do not have a span. It's not given here. The only thing that we know is it's a simply supported beam. That's all what we know. So, but we have two equations, and we can now eliminate the span from the two equations and to find QD. And QD is then, of course, equal to 2 times the shear force squared divided by 8 times the bending moment. And gives you 102 kilonewton meter per meter. So the capacity in outlet limit state P of the beam reinforced with minimum stirrups and minimum longitudinal reinforcement is for the bending moment 52, for the shear capacity 103, and for the load 102 kilonewton per meter.